Last time we started section 8.5, we were looking at equations in the Cartesian coordinate system. And we had talked about equations, graphing them, finding them given certain pieces of information. And today what we're going to move into is we're going to move into systems of equation. So systems of equations mean that we have a set of equations, usually with more than one variable in each equation. Now, the ones we're specifically going to look at are going to be two equations with two variables. Okay? You can use more, and that would be higher mathematics than what you guys are being certified to teach, so we're going to stop with two equations, two variables. A solution to a system of linear equations is an ordered pair that belongs to each one of the lines. So it is a point that lies on both lines. So it has to satisfy both equations. Graphically speaking, the only way that can happen is if the two lines cross one another or they intersect. So when we're looking for a solution to a system of equations, we're looking for their intersection. There are lots of ways to do that. We're going to look at the two that are most accessible. Maybe they're the easiest conceptually to do. Certainly the most accurate. One of the ways we're not going to look at, and it's often taught, is graphically. If I could graph both lines and visually see where they cross, that'd be super nice. And it works great as long as you've got things that are drawn very well. So you've got to have students that are going to draw well for you. And then you've got to have like grid paper. And almost without exception too, you've got to have equations that are crossing a whole number of values for this to work very well. So the two methods that we're going to talk about don't rely on our accuracy of drawing. We're going to look at the substitution and the addition method. All right, so the substitution method's our first one. The way this works is that you solve one equation for one variable. You substitute, hence the name for the method, you substitute this value into the other equation. At that point, there will only be one variable left, and you solve the resulting equation. You'll find one number then, so like x equals 4, or y equals 7. And you plug that number, or back substitute that number, into your answer from the first equation, and solve. You should check your solutions, at least mentally, by plugging both values into both equations. Make sure that they seem reasonable, that they work. And then we would always write the solution in an appropriate way. If we don't have any context, we're just given equations, we write it as an ordered pair. If our system, our context, or our problem has context, then we would include units. We wouldn't write it as an ordered pair because it wouldn't make any sense. All right, so we're going to do an example. We are going to do an example with context where we actually have to start at the beginning and create the equation that they're talking about. Okay? So here is our context. We have a movie theater. The child ticket for the theater costs $5 and the adult ticket costs $8. On Memorial Day, the theater counted 562 audience members and $3,785 in ticket sales. And this is fairly realistic. They would have probably counted, right? Counted to make sure everybody that came in, and they can see from the box office how much money was brought in, and we could actually be able to find how many children and how many adults came to see the show. Right? And that's what we're going to do. We're going to figure out how many children and how many adults came to see the show. Okay, so as we're doing this, the first thing that we have to actually address is we have to address the fact that there are some unknown quantities. I don't care what you call them. I tend to just use X's and Y's for everything, but if you want to use other letters, it's okay. Please don't use T, because it looks like plus signs, and please don't use S, because it looks like 5s. Everything else is probably okay. Okay? So I'm going to use X. So what are some unknown, and Y, actually, we'll need to. What are the unknown things in this situation that I'm trying to find? Yes, Alicia, you said that so well too. It's the number of child tickets. we have a tendency sometimes to write down something shorthand for that, and we'll write something like child tickets. But it's really the number of the child tickets that we're looking at, right? Yeah. What's the other thing that we're trying to find? Very good. The number of adult tickets. So these are the two quantities we're looking for. And the information in the problem will help us in creating equations that actually compare these two quantities, use these quantities. So one of the issues in the problem is we talk about how many people came in. So it says how many people total? 562 people total. How can I use my unknown quantities and the number 562 to create an equation that relates all three concepts? Agree. X plus y equals 562. Does everybody understand where that equation came from? Okay, great. That's the straightforward question because we're talking about numbers of tickets compared to the numbers of tickets. The other equation has to do with money. It says that a child ticket is $5, adult ticket is $8, and the total profit, or revenue rather, of all of our tickets is $3,785. So let's just pause for a moment and ask ourselves, if I sold 10 child tickets, how much money would I make off of child ticket sales? 50. And how did you get that? Right, you multiplied. You multiplied the $5 times the made-up 10 that I just created. That was a made-up number, but it was representative of the fact that there were X tickets sold for children. And the same thing works for the adult tickets. The adult tickets were $8, and if I gave you a made-up number of adult tickets, then you would just multiply them as well. So that would be 8y. This will get for us the price that all of the children's tickets were, the price that all the adult tickets were, and we know that when we combine them together, they will equal the $3,785 in ticket revenue. Does that make sense? Okay, so all of the work we've done so far has nothing to do with this method. No matter what method we did, you would have had to create these same equations, okay? Now that we have the equations, we are ready to go through this method. So the first step in our method is to solve one equation for one variable. Now, one of these equations is easy to solve for a variable, and the other one is not. Which equation is easy to solve for a variable? The first one. What makes the second one not so easy to solve for a variable? Yeah, there's a coefficient in front of both of my variables in the second equation. So let's take the first equation. So I'm going to write my steps out like this. You don't necessarily have to write steps out, but I just want to make very clear which ones I'm doing. So the first equation, which was x plus y equals 562, and I'm going to take that equation and solve it either for x or y, and it doesn't really matter which one, so we're just going to do x. So I'm going to subtract my y to the other side. So this would be x equals 562 minus y. Everybody good with that? That's step one. Step two says to take that value, take the fact that x is equal to 562 minus y, and plug it in, substitute it in for the x value in the equation. So right now you have 5x plus 8y equals 3785. And what they're saying is that this quantity can replace x. In other words, I can write my 5, and instead of the x, I can write 562 minus y. And the rest of it stays the same, plus 8y equals 3785. What would I do next to solve this? I mean, that is step 3 now, is I'm going to solve this. So what would I do to do that? Yep, distribute would be my first step. So what does 5 times 560 do? 2,810. Good. 2,810. And then I need 5 times negative y, so that's negative 5y, plus 8y equals 3785. Now, in the middle here, the negative 5y, the positive 8y, those can be combined. So I have my 2810 plus 3y equals 3785. Now what? Yeah, we'll subtract the 2810 to the right. So now I have 3y equals what? 975. What would I still need to do in order to find y? Yeah, I need to divide by 3. So what does y equal? 325, I think, yeah? Okay. So all of this is step 3, solving. It's the longest step, without a doubt. Step 4 says that we're going to back substitute. What does that mean? Well, it means that I'm going to find the other variable. So I'm going to take this 325 and I'm going to plug it in somewhere. I can put it into this equation, or I can put it in that one, and that's my favorite. Why do you think that this equation right here is my favorite to put it into?
Because it says x equals on it.
Yeah, it already says x equals. Yeah, that's exactly right. So I can use any of them. They'll all work, but I like that one to say x equals 562 minus 325, which is what? 237. Okay, so that's step 4. Step 5 is to make sure that it really works. So, in other words, real quick, you can do this with your calculator. Does 325 plus 237 equal 562? That's the easy one to check. Yes, good. The other one that we need to check, though, is we need to check the second equation. If I take 5 times 237 and 8 times, what was it, 325, does it equal 3785? Yes. So I don't necessarily have to see you write that down, but it's a good idea for you to check, and there's a couple of reasons. Number one, it's kind of like, you looked in the back of the book, right? That's the only reason you guys do that, right, is to check and make sure you got the right answer. So why wouldn't you want to check and make sure that you got the right answer from this? Same idea. If it's at your disposal, you have a way to do it pretty quickly, efficiently, why wouldn't you, okay? Also, that way, if you got the wrong answer, you can go back and find where your error is and fix it, and then you don't miss any points for it because you found your error. Now, the last step, if you will, we will do, it's number 6. It says to write the solution as an ordered pair, if you're just working with equations, or with units if you have context, and we got all kinds of context, right? What does the 325 actually mean, and what does the 237 actually mean? It's the number of tickets that we had, right? So we have 325 what? Was that adults? It was Y? Yeah, it was Y. Sorry, thank you. So this is adult tickets. And we had 237 child tickets. And that's our answer. So that's the substitution method. Okay, any questions on that one before we use another method? Okay. Elimination method. Some books will call this the addition method. You should just be aware that there's 2 names for this. Elimination, because you are eliminating a variable. Addition, because you are adding equations together. Step 1 says, if necessary, multiply both sides of the equation by a suitable number so that one of the variables will be eliminated when you add the equations together. So in other words, you want them to have the same coefficient with opposite signs, one of the variables. Step 2 is to add the equations and solve the remaining equation. And then step 3, 4, and 5 are exactly what they were before. 3 is to back substitute, 4 is to check and make sure that things work, and 5 is to write the solution as an ordered pair or a value with units. Okay, and again, I would like to do a problem with you that requires us to find our equations. So it doesn't start at the beginning of the steps. We actually have to create the equations first. And our example is about Cassandra. At a bake sale, Cassandra sells 4 muffins and 6 cookies for a total of $18. Michelle sells 3 muffins, 11 cookies for a total of $20. How much does a muffin cost? How much does a cookie cost? Now that's a little different setup than the last problem, right? In the last problem, we knew how much the tickets each were, and we were trying to find the number of tickets. Here, we know the number of the baked goods, and we're trying to find the price of them. So the setup is a little different. So I'm going to use my same x and y because I'm boring like that. What would x or could x be in this problem? Very good. I even like how you used the word cost. That's important. This is the cost of a muffin. So then, what could y be? Yeah, the cost of a cookie. All right, in our scenario here, we actually know the numbers of each of the things the person's purchased, or sold rather, and then we know the price, right? So if a muffin cost $3 and she sold 4 muffins, it would cost a total of $12. We would be multiplying, right? So it works the same way here. We have 4 muffins times the cost of a muffin. This is like the second equation that we set up over here with our ticket sales, right? The cost times the number sold, plus 6 cookies times the cost of a cookie, which is my y, and that's Cassandra, and how much money did she make? $18, yeah. What will Michelle's equation look like? $3x because she sold 3 muffins, 11y, she sold 11 cookies, and it equals 20. Now, in theory, not in theory, in reality, I mean, we could use that first method that I had, and we could solve one of these equations for one of the variables. But do you look at these equations, this set of equations, and see why that's not especially, like, appealing to do? I mean, all of these variables have coefficients, which means that if I try to solve for one of them, I'm going to get fractions involved. And that's going to be messy to work with. So in this situation, elimination it's definitely a preferable method. Now the elimination method on part 1, it says that I need a suitable number to get numbers to add up nicely. So if you take a look, our goal is to either get these numbers in front of x and thereby x cancels out, or these numbers in front of y and y cancels out. And what do we want them to be? Well, we want them to be the same value in opposite signs. So I'm just going to go with x's just because they're listed first. There's nothing special about that, but just because they're listed first. 4 and 3. What is the lowest value that I could multiply them and get to something they have in common? 12 would be the number, right? That'd be their least common multiple. So if I were to multiply 4, what would I need to multiply 4 by to get to 12? 3. And if I want to multiply my 3, what would I need to multiply my 3 by to get to 12? 4. Now if I do that, I'm going to get 12 on both the numbers, which is the hard part, right? I mean, like, that's the bulk of the work. But I really need them to be 12 and negative 12. So one of these has to be multiplied by a negative value as well. If they happen to already have one positive, one negative, fantastic. You've got one less step to do. This one just didn't. So what I'm going to do next then is I'm going to multiply each of these by the respective values. Actually, let me do this. All right, so if I multiply this, I have to distribute, agreed? And I have to distribute to all three values that are in this equation, the 4x, the 6y, and the 18. So on the first one, I get the 12x because that's, what I was going for anyway. What do I get for y? 18y. And what goes on the right-hand side of the equation?
24.
What is it? I think it's 54. It was equals 18, not equals 8. You might have missed that piece. Yeah. It's okay. So we have 54. Excellent. And on the second equation, I'm multiplying by negative 4. So again, as the goal was, I get my negative 12x. What do I get for y? Yep, negative 44y equals, and the last one's also a negative. Negative what? 80. And then I'm going to add down. So these two cancel. I have positive 12x, negative 12x, that's 0. Next one, I have 18y and negative 44y. What does that add to? First of all, it's negative, right? Negative 26y. And then 54 and negative 80 happens to also be negative 26. And then what would I need to do to find y? Divide by negative 26. Why would I divide instead of adding or subtracting? It's a good question to ask at this point. Why do we know it's division? Yeah, the negative 26 here and the y here are multiplied, and the inverse of multiplication is division. So because they are multiplied, I will divide. So divide by negative 26. So what does y equal? Magic 1. Okay, so all of this work over here to find my suitable number and so forth was step number 1. Step number 2 was all of this work to actually solve for one of the equations, the addition part of it and the subsequent cleaning things up, solving. Step 3 is to back substitute and find the other variable. Now, unfortunately, I don't have an equation that says x equals on this one. I just don't. That's not part of this particular process. So I usually have to work a little bit harder in this process to find the second variable. But lucky for us, we actually have the number 1, and that's friendly. So we're going to plug in 1 for y. So I'm going to use just the first equation. If you use the second equation, it's totally fine. I have 4x plus 6 times 1 equals 18. So 4x plus 6 equals 18. And then what? Subtract 6. So what does 4x equal? 12. And then divide by my 4, again because the 4 and the x are multiplied. What does x equal? 3. Okay, so we should check to make sure that this works. Y is 1, x is 3. So we can mentally, or use our calculator to do so, plug this in. So 4 times 3 plus 6 times 1. What does that equal? Does it work out to 18? Excellent. So that's sort of checking it off. Again, you don't have to write it down. Then you've got 3 times 3 plus 11 times 1. What do we get on that one? 20. And that checks out. So we've checked it either mentally in the calculator or on paper. And then our last step is to write the solution in this situation with context. What is x? What is y? So what did we find out is the solution to this particular question? Muffin costs $3 each, and cookies cost, or cookie costs, whatever, $1 each. That's our solution. Any questions on that one? All right, so we've done two examples now, and both of our examples have been ones that have one solution. One value for x, one value for y. That doesn't always happen. There are also actually three possibilities when we have a system of equations. They could have one point of intersection. And if they do graphically, that means that they cross one time. So visually speaking, it would look like this, right? They could have no solution. And for those of you who've taken number theory, this symbol right here means the empty set, and it means no solution for what we're talking about here, right? The solution set with nothing in it. So graphically, having no intersection, any idea what that would look like? They would be parallel lines. Very good. Or a system could have infinitely many solutions. And if that's the case, what it really means is that you had two representations for the same line. Two equations that if you simplified and boiled them down far enough, they would recognize that they're actually the same equation. Which means they have all points in common, is what it really means. So we're going to actually do some that are just without context now, so that we can help to identify when we have these situations arise. It says find all solutions, if any, of the following systems, and they give us no indication which method we have to use, which means we get to pick. So on this first one, would you like to use, the first question we have to ask ourselves is, would you like to use substitution or elimination? Both will give you the same answer, so we don't even all have to use the same thing, but for the purposes of doing it in class together, we're going to use the same thing. So which one would you guys like to use? Substitution. Okay. So if we use substitution, whoops, I thought I had my pen going here. The first equation we might as well use. Would you like to solve it for x or y? Y. You want to solve it for y? Okay. So I have x minus y equals 1. What would I have to do to get y alone? Subtract the x, right? So we'll move the x to the right. So now I still have a negative y, not y, but negative y on the left, and I have 1 minus x on the right. Then what would I need to do? Change the signs. Divide by negative 1, multiply by negative 1. It all means the same thing. The net result of any of that is that all signs will change when I multiply or divide by negative 1. So y is going to equal negative 1 plus x, or if you like to write the subtraction the other way, you can do x minus 1. Okay, so this is step 1 of the substitution method. Do you remember what step 2 said to do now that I have y is equal to x minus 1? Yeah, we're going to plug it into the y over here in the second equation. So I have 2 times x minus the new quantity x minus 1 equals 5. We do need to be careful on this one. What would we need to be careful of, do you think? Yeah, it's really easy to forget to distribute that negative. Super easy, so be careful. We will have 2x, and then minus x and plus 1 equals 5. 2x and minus x, those combine to be what? X. So now I have x plus 1 equals 5. And my last step would be to subtract the 1, so what is x? 4. X is 4. Okay, so that's the end of step, I don't know, step 2 and 3. Substitute and solve. So step 4 is to back substitute. So what we discovered when we back substituted last time is that there is in fact an equation on my screen that's nice enough that it's solved for the variable I'm still needing, y. So y is equal to x minus 1. So I've got y is equal to x, which is 4, minus 1, which is a grand total of, don't everybody say it at once, 3. Thank you. So this is step 4. Step 5 would be to check and make sure that it really works. right? If I do 4 minus 3, do I get 1? Yeah. If I do 2 times 4 minus, again, 3, do I get 5? Yeah. So this equations were straight enough that you probably could just do it really quick in your head. All right, so then how do I write my solution? There's no context on this. I don't have tickets and cells of baked goods and whatever. What is x? What is y? How do I write them properly for a solution? 4, 3 as an ordered pair. It is a point. It is not x equal 4, y equal 3. X equal 4, y equal 3 are two lines. One vertical, one horizontal. This is the ordered pair point. So this actually said find all solutions if any of the following systems. And what I want you to recognize is on this one there is one solution. So when there's one solution, you'll know it. Because when you're solving, it will become very apparent that you have one solution. Now our other example obviously is going to be one that doesn't have just one solution because I want you to see the difference in what happens when you don't have one solution. So we're going to do this one to see how that works out. Since we did one with substitution, let's do this one with elimination, okay? It won't make any difference. You run into the same error either way. So if I wanted to eliminate something here, the first thing hopefully that you recognized here is that the x's and y's are not lined up. Do you see that? Be careful, all right? It's not really meant to trip you up, but this one could trip you up very quickly if you didn't recognize that. So the first thing I'd like to do is to get these things to line up. So the first equation is 2x minus y equal 1. The second equation is actually negative 4x plus 2y equal 3. So we'll line up our variables. There are some books I've taught out of that actually uses that as step 1 for the elimination method. Line up your variables. All right, which variable would you like to eliminate, x or y? Oh man, so much to decide. Y, let's eliminate y. So right now, if I eliminate y, this is a negative y and this is a positive 2y. What number would I need to multiply and by which equation to get them to match? The top one by 2. And nicely enough on this one, the numbers, I only have to multiply one equation first. And one of them is positive and one of them is negative already. Agreed? So that's friendly. So if I multiply the top equation by 2, I get 4x is what I meant to say. 4x minus 2y equals 2. And what happens in my second equation? Well, it stays the same. Negative 4x plus 2y equals 3. So who said they wanted to, Casey, you said you wanted to get rid of x's, right? So Rachel said she wanted to get rid of x's. Casey said she wanted to get rid of y's, and what did we do? We got rid of both of them. That always happens when you don't have one solution. They both eliminate at the same time. So that's how you know that you don't have one solution. Now, how do you know if you have infinitely many or if you have 0, basically? Well, we ended up with 0 on the left. What's on the right? It's actually a 5, right? 0 does not equal 5, agreed? That's not going to work. This is not a true statement. So if it's not a true statement at the end, if you get 0 equals 5 or 4 equals 7 or something like that, they just are not equal, this means you have no solution. And that same thing will happen if you do elimination or substitution. If you're dealing with something that's got parallel lines, this is what it looks like. If you've got the same line, at the end, instead of it saying 0 equals 5, it would say 0 equals 0. Or 7 equals 7, or 46 equals 46. If that is what happens, then you have infinitely many solutions, and it's actually the same line you started with. Any questions on that?